Are we good? Yeah. Okay. Good morning. My name's Jen Castillo, and I'm going to talk to you about one method of designing an Android subsystem. I'm assuming the reason why you guys are here today is because you've been tasked to design your sensor subsystem. And your manager thinks it's just a matter of creating an awesome user experience and having a long-lasting battery. The problem is that those two items are on opposite ends of the spectrum. Ultimately, you need to tune in, dial in according to a million different little nuances in your design to create the right system for your product. That means on the user side, you have latency, gesture recognition, and sampling rate. Contributing to the battery performance, you have wake-up event processing, gesture processing, what your calibration strategy will be, and what the hardware or coprocessor design of your sensor architecture will be. So we're going to talk heavily about the trade-offs on all these different elements. But first, let's talk about whether you even need to do this. I refer to there really being two different types of products. The first is established products, which are ones that are working with the current state of the art. They're doing no more, no less. They're just trying to keep up with what everyone else is doing. The other is an innovation-driven one. And that innovation-driven one is trying to lead the pack. That means it's doing something new, innovative, and different. It also means it's a lot more risky. How do you know what you'll be? Here's a list of questions to help you guide you to whether you should, which type of device you're going to be making. If you're going to be making another device in another 6 months or several devices in the next year, you're probably established. If the reference design that you're currently looking at from your vendor, from your chipset vendor, is good enough already, you probably don't need to go through what I'm suggesting today. If you're innovation-driven, you have new types of sensors. Your features are generally more important than your release date. In fact, you may not even know what your release date is. It may not be gelled in yet. And resources and money really aren't a problem on your particular innovation-driven product. As soon as we use the word innovation, we're automatically assuming that there's risk. We don't know what the outcome will be. We don't even necessarily know what the scope will be. So answering these questions and let the number of yeses guide you to what type of product you are. Let's talk about the reference design. The reference design is great. A lot of stuff is already done for you. It's a lot like going along with the popular crowd. As long as you just do whatever the popular crowd wants you to do, you don't deviate from it, you're fine. The problem is once you want to do something new and innovative, you have to go against the reference design. And that can cause you problems. For those of you who like lots of bullet points, I was asked to put in the slide. If you go out on your own, you're on your own. The vendor is not going to be able to help you if you deviate heavily from the design. You're going to have integration pains. Every time they make a new drop, you have to integrate. That takes time. That may take an entire person in and of itself on your team to do. Your testing time's going to go up because you have to test everything that you've created, whereas taking whatever you've gotten from the vendor may already be good enough. So you need to have a larger QA staff. If you decide to make gesture recognition a focus of your product, you now need an entire team just to do gesture recognition, gesture collections, so you can then test them with your algorithms. Your calibration strategy will also take more time to develop because it's not being given to you by a vendor. And overall, you'll probably end up with a much larger mechanical footprint. Why? Because your design doesn't fit with the already optimized reference design platform. But going out on your own, you'll have a much stronger control over the overall power consumption, which means you'll more than likely be able to drive it down. You'll control the code size. The problem with the reference platforms is they provide a lot of stuff, but there's not necessarily that much time to go through and figure out what you can keep and what you can get rid of, what you can optimize, because it's not your code. It takes time to really understand code. You'll have a chance to control the mechanical footprint, but I guarantee it's probably going to be larger than whatever the reference design is. And finally, and this is probably the best reason to go against a reference design, you'll develop this in-house expertise, whether it's in gestures, whether it's in this new sensor type, it'll all be yours. That means when something goes wrong, and we all know it goes wrong, you'll be in a better place to identify where in the chain it broke and how to fix it. With a reference design, you may not have the know-how to do that, and you'll be entirely dependent on the vendor to do that. I don't think I mentioned this. When I refer to the reference design, I'm talking about the sum total of the intellectual property that the vendors deliver to you. That's schematics, software, test infrastructure, application notes. So here's your product in block diagram form. I've laid out the different layers. We're primarily going to focus on the hardware and all the trade-offs in there. It's consisting of the sensors, the sensor hub, and the coprocessor. That data is then pushed up into the Linux kernel. You'll have to deal with kernel interface drivers, sensor drivers, and then that data is then taken up through the libraries, through the sensor HAL, sensor services, and sensor manager. Above that, you have frameworks and application layer. I'm not going to say very much about those two layers because there's not a lot for me to add. Okay, let's get started on hardware. Your main goals are as follow. Once again, user experience and power consumption. For us, that usually means latency and power consumption. Latency is really used interchangeably with user experience, at least when you're down at the low levels, because it's very easy metric for managers to grab onto and note progress. If you have a log latency, let's say, how many of you have used your phone, particularly with some of the earlier Android phones, and when you rotated the screen, there was a couple seconds delay? Yeah, that's a long latency. And it can be frustrating because you want to move on and keep doing whatever you were doing. Once you understand that it's a long latency, you'll understand why you want to shorten it to increase the user's positive experience. Power is the second, is the other end of the spectrum. Power in the current state of smartphones is a lot like vampires. We have to keep them plugged in often. You know, we have to feed them frequently. And how many of you have to keep your phone plugged in at some point during the day? Particularly the Android ones, right? Especially if you're using your phone. If you're just using it to like collect, to answer messages, not a big deal. But if you're checking your email, if you're twittering, then you need to use your phone, and then you're probably going to need to have it plugged in at some point. The other thing I want to point out before we get too much into this is when you're selecting hardware, understand that every time you decide, hey, we're not going to have the hardware do this, we're going to have software do this. This puts a lot of stress on the software team. Every time you decide, we're not going to buy this part, we're going to have software implement it in the design. You'll have to understand that they may not have enough space, they may not have enough processing power for what you're asking the software team to create. Let me try that again. If you don't make it, or if you don't buy it, you'll make the software team make it, and they may run into code space issues and processing power issues. Also, you can save a couple cents on the BOM. With these in mind, your two main goals for the hardware, at least down at this low level, is you need to figure out your sensors, and you need to figure out how you're going to process and consolidate that sensor data and get that up into the rest of Android. There are not that many types of Android sensors. You have your typical accelerometer, gyro, mag, pressure, light sensor, proximity. There's a couple of other ones. So you don't have that many choices. If you decide that you have a new type of device, new type of sensor, you're going to have to plumb that data. You're going to have to alter the frameworks in Android to support it. And ideally, what you'll want to do is leverage any of the current APIs that exist in the framework, so you don't have to change it too much. Once again, once you do that, you're going to have to either release your own SDK for your device, or you're going to have to convince Google to take that as part of the regular code base. In order to select your sensor, you need to determine, you need to start keeping track of what its latency and what the power consumption is of each sensor. I suggest keeping a very large spreadsheet of all this data. You're going to be using it later on. So let's tackle what we can perceive of as latency. Well, let's look at the sampling rate. Generally, your sampling rates in Android, there's 4 different types: normal, UI, gaming, and fastest. The ones you're mostly concerned with are normal and gaming. Normal usually ranges about 5 to 10 hertz. Gaming ranges anywhere from 20 to 100 hertz. The higher the sampling frequency, the more power you're going to consume. The other thing that I've recently found out is that the OS, the Android OS that you're using matters. If you're using Gingerbread, you're still in that 5 to 10 hertz. Once you go up to Ice Cream Sandwich on these sensors, they're sampling at the normal rate of 15 hertz. So that's providing a much richer user interface, nice, smooth response, but it's consuming a lot more power. So let's look a little bit more closely about sampling, whether you should oversample, undersample. As I just mentioned, the more you sample, the smoother the response, the richer the user interface will be. But you're going to consume a lot of battery power. On the other side of that, if you don't sample enough, your users will be frustrated because it's taking too long to get the data. It will be inaccurate. They'll, your system will miss nuanced gestures that they're doing as a result. But you might save some power. It's probably not worth it. My advice is early on in your research, start tuning. Figure out what that ideal rate is. Another thing to note is that your sensor vendors, it used to be a lot of them would provide you with multiple sampling rates that they were using that was configurable in a register. A lot of them are starting to go to 2, maybe 3 different sampling rates instead of 4, 5, and 6 because they're under the assumption that customers want more limited choices. Ask them if they still support a wider range of sampling rates because it's quite likely they're just masking out information from you in those data sheets. Yes?
Just as a reference point, do you know what the sampling rate is for an iPhone in general, 4S?
Unfortunately, no. Do you know what the sampling rate is?
No. Anyone else? I mean, just as a reference point, when you're talking about user experience in Android,
Yeah.
the ice cream sandwich, having it default to a higher sampling.
Yeah. Usually you want, for gestures, as soon as you involve humans, you want to sample at about 10 milliseconds at least. The limit is about 30 milliseconds. Before it becomes really awkward for users. Okay. Any other questions? Okay, just confused faces? Okay. Now that we've looked at what the sampling is, looked at the sensors, let's look at how we're going to get that data in. Is that going to be pull-driven or inert-driven? Most of the reference designs are pull-driven. Pros are, it's really simple. If you're used to single-threaded applications, this works awesome. If you have sensors that are oversampling, you can throttle the data using this. You're essentially forcing an undersample or a decimation. Cons are you're going to have to manage your sleep processes more frequently. You have to figure out that strategy. Your latency is going to go up, and you might be losing data. Because of the latency and data loss issue, you will be checking the error registers on your sensors more frequently to see if there's an overrun or other type error. If you go to interrupt, you're going to utilize that low power sleep mode more readily. You're going to use less system resources such as timers. Cons are, and I don't think this is a very big con, if you're comfortable with writing ISRs and multi-threaded applications and sharing resources among multiple threads, this complex program structure con is not very much of a con. Okay. How are we, over what conduit are we interfacing these sensors? Most popular ones are I2C. Why? You can use 2 pins, and you can attach as many devices as you'd like, and they're individually addressable. Especially if you're trying to pack everything in on your design, this works really nicely. Other choices are A to D. You can use other serial interfaces. You can also even use parallel interfaces, albeit I highly doubt that any of you are looking at parallel interfaces. One question that you should have for your vendor is whether they support hierarchical structures. What do I mean by that? Well, on the right, you have the processor connected to each one of the sensors directly. So that's a very flat, I wouldn't consider that much of a hierarchy at all. Very flat structure. That's what most reference design vendors' designs provide. The hierarchy on the left is really only directly connected to sensor A, and behind it there's sensors B and C. Why is anyone doing this? Well, some of the sensor vendors, InvenSense most notably, is using these sensors such as B and C to perform a minor amount of sensor fusion to create better data. They're also consolidating that data and making it so you can easily get all 3 sensors data immediately without having to do separate transactions. The advantage is you may not have as much transfer overhead. You've offloaded the processor a little bit, maybe. The downside is if sensor B or C down here has a problem and you need to reset it or address it in some way, you now have to go through another sensor. It's not a big deal if your system is very reliable and doesn't break down, but if it does, this is a minor con. Okay. So wake-up events and processing, they're becoming much more popular these days. It used to be, and when I talk about a wake-up process, imagine your boss who told you you're going to make this sensor subsystem. If it's decided that the new gotta-have killer feature is shake to wake, now all of a sudden you need to figure out how you're going to do that. It used to be the designs were primarily your application processor was directly connected to all your sensors, which meant that your application processor never really slept. And because it's the most power-sucking chip on your entire board, your battery would drain very quickly. Currently, vendors are supporting this internal coprocessor design. It's reference supported. Most of the work is done for you. The processor tends to be an ARM7, maybe an ARM9, a Cortex M3, a 32-bit processor of some kind. It's not bad, but we can do better. You can use an external processor that's going to impact your footprint, but you can have whatever processor or microcontroller you want. So you can go down to a 16 or an 8-bit processor, or controller rather. You can control the outcome. You can customize it however you want. You just have to understand your footprint design, your mechanical design is going to take a hit, and you're going to be asking for a lot of extra work, particularly at the software level. When you start looking at the different processors that you could use for this external processor design, you need to start talking to your sensor vendors because they have algorithms. They have, most of their stuff is their secret sauce, is their algorithms for gesture detection or calibration. I highly doubt they will give it to you in source format. They will only give it to you in binaries. You want to make sure that they're going to support whatever processor that you have, because all they're going to give you is a binary library to compile into the rest of your work. So you should check with them very early on this. Just pointing out that once you come up against the external processor and you start noticing all the work that's going to go into it and having to manage even just the relationships with all your different sensor vendors, that may be enough for your management to decide to nix this particular design choice. Okay. So now that we're evaluating your sensor hub, that's what I'm going to call it, sensor hub, you need to figure out whether it's going to be internal or external, and you need to decide what the criteria is going to be. It's going to be latency and power consumption. And you're going to be evaluating all those extra low power modes. Make sure as you're going through this that your software team is comfortable with the code size and features that will be packed onto this particular processor. Okay, we now have a gigantic spreadsheet full of all the sensors and application processors, or not application processors, sensor co-processors or sensor hubs that we may want to use in our final design. But how do we evaluate it? For each solution, we want to sum up all the sensors, power consumption, as well as any dedicated processors we decide to use. We also want to add up the latency by taking the max latency from any one of the sensors plus its dedicated processor time. Once you have that, you have sensor solution A. You'll want to do this so you have multiple sensor solutions. That way you can compare and contrast them. If you have a close call and you can't decide which one to use, make sure early on you identify tiebreaker criteria. That can be something as easy as, hey, everyone on the team has designed with this processor before, or there's pre-existing work in the company that will expedite our design process, or there's a cost or footprint implication that's good and basically tip the scales one way or the other. Okay, Linux kernel. Now we're actually getting into stuff that maybe is not so boring. Kernel drivers. Most of your kernel drivers for the interfaces you're going to use are already existing in the kernel driver. So whether you're just going to directly interface each sensor, or whether you're going to have your microcontroller interfacer or your sensor hub, as I'm calling it, that peripheral driver should already be there. If you decided to go with a coprocessor, there is probably a shared memory API that your reference design already has. Make sure you refer to the application note early on. Okay. Libraries and services. Your primary focus here is to determine where your gesture and calibration algorithms are going to go, because in most cases they end up in the library section in your sensor service. But before we get to that, make sure that you've implemented your HAL. This is probably where you have your platform or BSP team working. It's located in your device, vendor name, board name, libsensors. Some reference designs are now putting that in their vendor directory. I'm not going to tell you how to design a HAL on there. There's plenty of examples, most notably the Samsung Crespo one that's for the Nexus S that provides an excellent baseline for you to work from. Other places. Your sensor services are located in the frameworks, base services, sensor service, and the sensor manager. Okay. So let's, before we dive into more about where to put the gestures, let's talk a little bit about sensor fusion. What is it? It's where you take any two disparate sensors and combine them as a way to get more accurate, robust, or dependable data. You can do sensor fusion almost anywhere. You can do it at the sensor level, at the sensor hub level, the Linux kernel, or libraries. Most people are doing it in the library level because you have more processing power there. So this is just reiterating what I just put in the last slide. You can do it at that sensor service level, which most reference designs support. But you can put it down in the sensor hub. Some reference designs support that. You'll have to work with your different sensor vendors to basically pull in the algorithms to work with your reference design. But if for some reason you decide to put it in your sensor hub, your external sensor hub, and you don't have vendor support, how do I put this delicately? You could try porting it, but there's a lot of overhead doing that. One, you're usually moving a 32-bit set of code downward into maybe a 16 or 8-bit processor, and that gives you all kinds of troubles. Most immediately is all of a sudden I need to cram 32 bits of data into 6 or 8 bits. So there's all kinds of alignment and architectural issues there. Next, there's a lot of complex coding, such as matrix math, multiplications, and divisions. 8-bit microcontrollers are not set up to effectively do that quickly. You may run out of code space just on that portion alone. So you'll have to spend time optimizing for that. In addition, any algorithms may have floating point. There's no floating point in microcontrollers. This all adds up to, if you decide to embark on this, you'll have to spend a lot of time testing and benchmarking and seeing if you're anywhere near where the goals are. Because if you decide to do all this complex math, perhaps you decide to put it into a lookup table, or you decide to do some sort of a mathematical approximation. Either way, there's going to be enough deviated error that you may have to retune and retest your gestures. Okay, so let's summarize that. Gesture detection. You can make or buy it. If you make it, you're offloading your application processor and pushing it down into some cheaper processing power. You're going to expand your in-house expertise in this area, and you might end up with more compact code. If you buy it, minimal schedule impact, it's already tested and tuned, and it's probably a pretty complete solution. Where should you place your gesture recognition? Application processor, it's very powerful. Most of the work's already done. It's reference supported. Your sensor hub, it's very cheap power, very cheap processing power, and you'll be able to handle wake-up events. Okay. Same type of problems happen with calibration. Usually with calibration, though, in order to stay calibrated, they usually have a sampling rate that they need to have met in order to meet that accuracy level. Maybe your product doesn't require that much accuracy, so maybe it'll tune down its sampling rate during dead spots and then ramp it back up over time. You should check with your vendor to determine what that sampling rate is in order to keep minimum accuracy. Another option, if you're optimizing more heavily for power, is to stop sampling altogether and instead ask your user to do a gesture as a way of calibrating. And that's only right before they start using that critical sensor system. The impact is, well, do you really want your users to do this? Your UI, UX people will probably flip. Other considerations, just to wrap up. You need to be creating tests at every point along the way, at every level. You need to create tools to allow you to program different, if you have an external sensor hub, you need to create a mechanism for programming that through your application processor. So once again, you need to create different checkpoints at every level of the system. Why? Well, if something goes wrong, you need to be able to quickly identify where the problem is. Your reference designs, they vary on what they do here. Some of them give you, excellent tools at every level to help you identify problems. Others just give you an Android application to say, hey, it works end to end. If it doesn't for you, well, we don't know what's wrong. So that's why it's important to create those tools. For the sake of bring up and allowing your QA to script things more effectively, make sure that you have a tool in place so your application processor can talk to each one of your sensors. I can't stress that enough. Become very familiar with the CTS. I've listed here the path to the one that's applicable to the sensors, to the sensor team. There's also one for the sensor services. Check that one out. And then finally, your reference design usually has a ton of information on how to do manufacturing tests. In fact, it may already have a test harness readily available for you. Check it out early, see what you can leverage. That way your EVTs are not left last minute and you're just trying to struggle to come up with a process weeks before you make that run. At this time, I'd like to open the floor for questions. Yes, you.
Do you really notice much difference when working with the data development kit with sensors versus working with just the standard Android stack? So you're actually getting faster sampling rates or anything like that?
Most of the sampling, so since I work heavily, as you can tell from my presentation, I work extremely down at the low levels. Have I noticed much difference? Honestly, no, but I haven't had very much experience either way at those upper levels. Yeah?
With design ICS, can you lower, is there anything less than normal? Anything less than 15? And the other question is, what are the differences between the job, between the ICS compatibility? If we work on gingerbread sensors, what will be our major challenges switching to ICS?
Let me think about that for a little bit, because I'm right in the middle of an ICS migration. So what I've noticed, so what I was told by my vendors were, oh yeah, it's going to get sampled more heavily. So you're going to have much more throughput. If you are already at the limits of your processing power in your gingerbread implementation, you're probably going to hit them pretty quickly, which is why it's really important to not let schedule creep or scope creep come in on your product, because what you originally scoped for a processor or a product that was gingerbread based was fine, but once you get to ice cream sandwich, everything really changes. So you'll immediately spend more time tuning. But what I did find was in one of the HALs I was working with, one of the HAL examples is that they actually had a place where you could set the rates. So you could set the gaming, UI, normal, fastest, you could set them. But I don't have much more to say about those, fortunately. We can talk about it afterward. Anything else? Yeah.
So besides changing the sampling rates, any other measures to reduce the power consumption?
Other than tuning the sampling rates, your option is always just to turn off the sensor if it's not being used. Especially if it's not being used for a wake-up event.
So sampling rate is currently the only way to adjust the power consumption, right?
For the impact on sensors, yes. How it can impact the sensor hub, there are other things you can do. But maybe I'm not following your question.
For the sampling rate, do we always stick to the same sampling rate, no matter the target is active or sleeping, or we change the sampling rate all the time?
That is something very specific to, if I understand your question correctly, that's very dependent on what your sensor hub is going to do. So whether that's the internal or external processor we're talking about. Some of the reference designs will, if they're not using that sensor, if no one's requesting that data from the application processor, they will turn off the sensors. They will turn off each individual sensor in some cases. And that's the way that they conserve power. They also, if there's not an active listener in the reference, at the coprocessor level, they will start putting themselves into sleep mode. And there's different levels of sleep. What will happen is they manage their sleep, and it's dependent on whose design you're using. It may be they have someone else waking them up. They may have their own timer to wake them up. They may have a wake on interrupt event that may be occurring. But it's very dependent on the software and how it's being used. Other than that, I'm not seeing that much with sensors trying to focus more on power consumption. A lot of that onus is put on us as designers to check that stuff out early during our research phase. Did that answer your question? Okay. Anything else? Thank you very much for your time.